Okay, thank you. So first of all, thank you for letting me present the results of a paper we published last year. The first author is Marco Mignoli, and is essentially the first spectroscopic confirmation of a large-scale structure around an early supermassive black hole. So here you see the website where you can also see and get some information about it. And in the background of the slide, you see an artistic view of the structure that comes from the ESO press release, where you see the bright quasar at the center, and also the 6 companion galaxies that we discovered. So Roderick mentioned this issue earlier today in his review, and essentially we think, although we have no proof, definitive proof, that early supermassive black holes, so objects of 10 to the 8, 10 to the 9 solar masses at redshift 6, likely form and grow in large dark matter halos. We have some indirect evidence based on the mass of the host galaxies. So the hosts have something like a few times 10 to the 10 or 10 to the 11 solar masses at redshift 6 already. And such a massive host should be hosted by equivalently massive halos. So for a galaxy of a few times 10 to the 10 or 10 to the 11 solar masses at redshift 6, halo mass of the order of 10 to the 12 or more should be at place. Another indication that these objects may live in particularly massive halos comes from the large number of companion galaxies that ALMA has discovered at scales of 100 of physical kiloparsecs or even less. And if you extrapolate the level of clustering needed to explain these numbers of companions to large scales, again, you end up with masses of the halo of the order of 10 to the 12 or so. Simulations also generally predict that such objects must form in dense environments and around massive halos. Here you have an example from Thiago Costa. So on the left, you see a simulated overdense region where you see the big black hole, the big black dot at the center, living in a halo of 10 to the 12, surrounded by galaxies which also host black holes in them. Whereas in an average density region, such structures are not found, and bright quasars, redshift 6, are not found. So these structures should extend for a few physical megaparsec, should host a large number of companion galaxies. So people over the years has tried to find them in many ways. So despite we expect a large number of companion galaxies, the searches for galaxy overdensities around early quasars have been, at the moment, mostly inconclusive. Most of the searches have been done on scales of about 0.5 up to 1 physical megaparsec around the quasar. And this case, even simulations say that you may have a large variance in the number of objects expected, partly because the possible feedback effect that quasars may produce, again, on very large scales of the order of up to a physical megaparsec. So a possible idea to track this overdensity would instead be to go to larger scales, above 1 megaparsec or so, or as you see in this figure, between 1 and 5 megaparsec physical from the center, where you still expect a significance over density. And so also based on the fact that now some of these large systems have been found at redshift 6, in the past we also tried to inspect large scales around the quasars. So in particular, it's now a few years that we are studying the field around this object, SDSS J1030 at redshift 6.3. It has a mass of 10 to the 9 solar masses, the black hole. And we selected over a field of view of 24 by 24 arc-minute around the quasar, about 20 Lyman break galaxies using the LBC down to the limiting magnitude of 25.5. So the field we are inspecting corresponds to separations on the sky of about 5 physical megaparsecs from the quasars. So we stacked, as a first step, the photometry of our candidates, and the stacked spectrum has a nice shape resembling that of a Lyman break galaxy at redshift 6. In imaging, the overdensity comes out with a level of 2.4. So it is again, and it was significant at more than 4 sigma, but obviously you really need spectroscopy to claim anything about the structure. So we tried spectroscopy essentially with every instrument we could apply for. So we used the Keck, we used the VLT, we used the LBT, and in the end we were able to measure the redshifts for 6 objects that are close in space, in redshift space to the quasar. So in this figure on the left, you see the distribution of the Lyman break galaxies around the quasar, these red dots, and in blue, you see the ones we confirmed spectroscopically at redshift 6.3. We also used the archival Msun data that were available on the quasar itself, here it is, and based on those data, we discovered 2 Lyman alpha emitters, again at redshift around 6.3. One example of spectra we got is shown on the left. This is a spectrum from the Keck where we see a break corresponding to redshift 6.3 that was later confirmed by a detection in the sublimiter of a carbon plus line from NOEMA. So this was the first of the Lyman break galaxy candidates that we confirmed spectroscopically. And then with the more spectroscopic data, we were able to add more candidates. You see again here other examples. This is based on mods at the LBT. This is based on Muse, where you see the clear Lyman alpha line emerging from nothing. Essentially, there's no continuum in this source. And in the end, we summed up the 6 galaxies, 4 LBGs by selection and 2 Lyman alpha emitters in the redshift range that you see here, between 6.2 and 6.35. And in redshift space, this separation corresponds to about 5 physical megaparsec, which is exactly the separation in projection that we have on the field under investigation. One interesting thing is that if you look at the spectrum in mods, for instance, you see that the spectral range, most of the spectral range, maybe 30% or even more, is blinded by strong residuals from the skyline subtraction. So suppose this line would have fallen at the redshift of 6.33 instead of 6.32, then we would completely have missed this object. So this to give you an idea of how difficult it is to get such systems with optical spectroscopy. So summing all of this together, we were able to collect this histogram, which is essentially what gives us the overdensity significance level in our field. So in the top panel, you see the histogram based on the Lyman break galaxies. In the bottom panel, the equivalent histogram for Lyman alpha emitters selected Muse. And the interesting thing is that the peak that we see in the distribution is at 6.3, whereas the selection function of Lyman break galaxies would have expected a peak at redshift of 5.7 or 5.8. You see, I don't know whether you see the cursor, but all these gray lines here are essentially the selection function of Lyman break galaxies using different color criteria, but all of them essentially would have expected a peak at redshift 5.7. Indeed, we found some of them there, but the most prominent spike is where you do not expect it, and it is exactly at the redshift of the quasar. So in summary, the overdensity level that we measure for the structure is of the order of 1.5 or 2, that we assess it as a lower limit. And this overdensity is distributed over a very large volume of about 800 physical megaparsec cubed. And the statistical significance, again, we estimated it in a conservative way and is of the order of 3.5 at least. Based on these numbers, so based on the overdensity measured in the volume that we probed, the clustering between the quasar and the Lyman break galaxy that you need to explain such overdensity in such a volume tells you that the halo in which the quasar resides is of the order of 10 to the 12 or more. And you can have a look at the paper for more details on these computations. So essentially, the main conclusion of this work is that we discovered for the first spectroscopic overdensity around the redshift 6 quasars, and we think that probably the failures that have been faced in other fields maybe are related to observational text limitations. So the obvious next steps are to move from the discovery to the physical characterization of the structure around this quasar. And also the other step is to discover more structures around early supermassive black holes to confirm theory. So let me just discuss the first of these 2 points in my final slide. It is related to the future programs that are ongoing in this field. So we are trying to follow up with deeper imaging to get a sample of the order of 100 Lyman-Break galaxy candidates around the quasar. We proposed for mu spectroscopy, for ALMA spectroscopy of Lyman-Break galaxy candidates, and also we have invested in asking HST and channel time. This field is actually becoming a very deep extragalactic field. It allows discovery of other interesting structures. So, for instance, I invite you to listen on Friday to the talk by Quirino D'Amato about the redshift 1.7 protocluster in the same field discovered serendipitously. And notably, this field around J1030 is part of a GTO time proposal with James Webb that will investigate overdensities around 6 redshift quasar at high redshift to trace overdensities using the oxygen 3 and H beta line. And this is my final word, and thank you very much.